The human brain is a warm, wet, and thermally noisy physical environment, strictly governed by standard biological constraints. In this specific environment, quantum decoherence occurs with extreme rapidity. Decoherence is the physical process where a quantum system loses its distinct isolated properties through interaction with its surrounding environment. Physicist Max Tegmark calculated that quantum states in biological tissue collapse in approximately 10 to the negative 13th seconds. We call this the femtosecond scale. Conscious decision-making operates on a completely different timeline. Empirical measurements of neural activity establish clear timing windows for human choice. Researchers Thura and Sizak identified motor commitment signatures occurring at approximately 280 milliseconds. Rajan and colleagues measured will detention deployment at exactly 300 milliseconds. The limit readiness potential begins approximately 550 milliseconds before a physical action. The limit readiness potential is a measurable buildup of electrical activity in the motor cortex that precedes voluntary movement. Compare that half-second window to the femtosecond elapse rate of a quantum state. Deliberate. This specific temporal mismatch invalidates any theory requiring quantum coherence to be sustained long enough to influence a macroscopic neural outcome. This dynamic logarithmic scale charts time to illustrate the magnitude of the problem. The mathematical difference between a femtosecond and a single millisecond is a factor of roughly 1 trillion. We are looking at a 12 order of magnitude gap. This represents an unbridgeable temporal hierarchy in physics. Thermal noise actively destroys superpositions trillions of times faster than neurons can complete a single firing cycle. A superposition is the ability of a quantum system to exist in multiple states simultaneously until it is measured or interacts with its environment. No known physical or biological process can bridge this specific mathematical disparity through simple dimensional scaling. This timing gap operates as a strict empirical constraint. It explicitly prevents vague appeals to quantum effects in theoretical neuroscience. Theorists are forced to provide exact specifications. They must identify the exact quantum states involved, their precise persistence duration, and the specific neural interaction timescale. Any theoretical model must identify precise mechanisms that survive this mathematical objection, or admit that the quantum interface in the brain is undemonstrated. If superpositions vanish before a neuron even begins to register a change in ion polarization, quantum mechanics cannot dictate conscious choices under standard models. The first major attempt to cross the gap comes from ORCH-OR theory. Orchestrated objective reduction, or ORC-OR, is a theory proposing that consciousness originates from quantum computations inside cellular structures called microtubules. This theory carries an absolute requirement for sustained quantum coherence until a gravitational self-collapse occurs. Tegmark's original decoherence calculations modeled superposition separation distances and thermal equilibrium within the brain, arriving directly at the femtosecond baseline. Researchers Hagen and Bandyopadhyay challenged Tegmark's parameters, argument he used unrealistic superposition separation distances and incorrect charge models for biological tissue. This vertical bar chart compares those initial decoherence times against the newly calculated estimates. Using mathematically corrected biological parameters, the revised timescale reaches approximately 100 microseconds. This revision narrows the timing gap by a massive 7 orders of magnitude. However, we must contrast this microsecond estimate against the required 280 to 300 millisecond decision windows established by empirical measurement. Revising the biological parameters delays decoherence, but a microsecond timescale remains wholly insufficient to influence will detention. This leaves the ORC-OR mechanism highly vulnerable. Physicist Henry Stapp proposes a deliberate theoretical pivot that completely discards the requirement for sustained coherence. He uses the quantum Zeno effect. The quantum Zeno effect is a phenomenon where repeatedly observing a quantum system rapidly enough freezes its evolution, preventing its state from changing. The core mechanic operates through discrete, instantaneous observation events. Instead of maintaining a single coherent state over time, the effect bypasses the timing gap by accumulating influence through rapid repetition. Mathematically, approximately 1,000 discrete observation cycles operating at microsecond intervals effectively span a complete 300 millisecond decision window. This has biological precedent. researcher Michael Denton demonstrated xeno-mediated coherence protection in cryptochrome proteins, proving the mechanism operates in nature. But this theory carries a specific phenomenological cost. The repetitive observation required by the xeno effect would cause sustained conscious attention to feel physically effortful to the individual. The xeno effect mathematically bridges the gap without requiring sustained coherence, but it demands a continuous mechanical intervention that shifts the burden from physics directly onto human phenomenology. Matthew Fisher proposes an entirely different class of mechanism, relying on phosphorus-31 nuclear spins inside Posner molecules. Posner molecules are symmetrical calcium phosphate clusters that theorists suggest could isolate and protect quantum states within the brain's noisy environment. The predicted coherence times for these nuclear spins range from hours to potentially an entire day. This timescale vastly exceeds any neural decision window, completely sidestepping the temporal constraints of the timing gap. But this diagram illustrates the fatal flaw of the exemption. Surviving the timing gap is irrelevant if the shielded quantum system is too isolated to communicate with the surrounding neural network. Subsequent analysis derived shorter upper bounds for this coherence, though the revised numbers remain mathematically longer than necessary for neural processing. The nuclear spin model solves the problem of time by creating a problem of isolation. Quantum coherence is only useful if it demonstrably influences macroscopic neural computation. The Unfinishable Map outlines a preferred framework for resolving this, post-decoherence selection. This requires a conceptual shift. The timing gap problem only exists if consciousness requires coherent evolution to operate. There is a critical misunderstanding regarding the measurement problem in physics. The measurement problem is the unresolved question of how and why quantum probabilities collapse into a single definite outcome when observed. Decoherence does not solve this problem. It merely suppresses quantum interference. Immediately following thermal decoherence, the system remains in a classical mixture of multiple possible outcomes. Something external must still determine which becomes actual reality. We propose that consciousness operates exactly at this point, at the instantaneous moment of measurement, rather than during the preceding coherent evolution. By operating at the exact moment of collapse, the duration of the prior coherence becomes mathematically and physically irrelevant, shifting the question from how long does coherence last to what determines the measurement outcome makes the theory entirely immune to the timing gap. The broader philosophical stakes are high. If the timing gap eliminates all quantum consciousness mechanisms, it eliminates the physical grounding for libertarian free will. Libertarian free will is the philosophical position that human beings possess genuine, unpredetermined agency to choose between multiple possible actions. This schematic visualizes how post-decoherence selection preserves the quantum opening for genuine agent causation. This mechanism allows consciousness to actively bias which specific outcome becomes actual at moments of genuine biological choice. This framework requires a strict cosmological assumption. It categorically rejects all many worlds interpretations of quantum mechanics. The many worlds interpretation is a theory suggesting all possible alternate outcomes are realized, each branching into an actual, separate universe. Under many worlds, there is no collapse and no outcome selection. This completely dissolves any functional role for consciousness. The timing gap serves as a necessary, rigorous empirical constraint. It forces theoretical discipline and punishes vague appeals to quantum mysticism. To understand agency, we must stop modeling consciousness as a state that endures through time. We must recognize it as the fundamental selector that operates at the precise mathematical point where reality collapses.